This topic is about immersion signal integrity study optimizing. I'm Kai, work at Intel. We have a new join, a new blood. Terry Little is a development engineering manager from Foxconn Interconnect. He's really in charge of cutting edge OSIP 224 gig development. We also have Austin. It's bring a lot of the system level experience, and Andy is a CTO at PureTest. So from day one, the signal integrity work for immersion has been figured out how to make the data center, the platform work in immersion with the minimum cost added to industry and to fit most of the liquid available from one single phase to two phase. This has been the goal of the signal integrity, minimum cost added and fit all the liquid. So we have 3 steps. First is understand dielectric performance of most of the liquids. So we have updated this table. This is not a spec, but rather update for the value. Why we update? Because the industry has improved the measurement accuracy. It's called liquid cavity resonator method. It's the same method people measure the PCB dielectric material. It's very reliable. So we are happy to update this table for the industry to look into. Second is system test. Is what really the margin impact from the immersion. As we can see the DDR. We test all the way from 5666 to MRDIMM 8800, which is fast. The fastest DDR you can find. We have small data value, but small data samples, but good enough data to show its minimum impact. And the PCIe we tested 5. Gen 5 and the Gen 6 is on the working in progress. Optics, they need to be sealed, and the reliability is undergoing. Testing focus, we focus on the Ethernet 112 gig PAM4. We also want to future focus on the 224. They are really fast. That's why we have the Terry here. Really fast. 112, 224 is a cutting edge speed. Thank you.
Okay, thank you, Kai. So the next portion I'm going to talk about is how we can consider the impact and the fixturing on how we're going to test this device, right? How we're going to test the device under test, or the DUT, right? So if we look at, well, we started out. Back then, everybody thought, well, okay, we just put the DUT in the fluid tank and see what comes out. Well, there's a lot of effects on this, right? The attributes being the SMAs. And then there's the traces on the board, especially if they're microstrip. So what we decided to do is see how we could encapsulate the first variable, which is the SMA. So you can see the picture below the fixture. And if you look at the picture on the top picture is actually in a very large tank that we have, that we can control the flow rate, we can control the heat, but that yellow line is just a dotted line, and that's the fluid level top. So this is a PCIe chem connector and an add-in card. So the interesting part is the add-in card was up out of the air, out of the fluid in the air, so there was no influence of any issues there. The chem connector, however, underneath had cable attached to SMA. So we had to figure out, if you look at the SMA in the picture on the left, it's about a 25 ohm drop. So the first thing we thought, okay, let's try to encapsulate the SMA. So we did that. We added shrink tube, and we put some, kind of epoxy around the area that came, and you can see in the picture on the right, that solved that problem. What it didn't solve is the impact on the traces, the microstrip traces. You can still see it's about 5 ohm difference there. So that has an effect. Even after de-embedding, we couldn't get rid of all the ripple. You see the picture on the top in the insertion loss. So that's really one attribute we needed to figure out. How are we going to take all these variables out of the equation so we can just look at the connector, right? So we came up with a kind of a cool, innovative idea, and we want to share this as a contribution as like a BCAM or something where you can isolate the DUT. So this is actually QSF-PDD, and you can see that the white portion is like a 3D printed top that has a trough in it. Now think about that. If you look at that, the MCBs now are inserted into the fixture, right? And the DAC cable plugs in from underneath. There's a pass-through, right? So what we did is we now put the fluid in the tank below, drop the entire assembly down into it, and then we seal everything off, you know, with the same type of epoxy, or I'd say more of a silicone. We let it cure about 24 hours. So now we have a sealed environment that only the DUT is in the fluid. And the next day we come back, you can see in the picture of the 3D model, the transparent view, that shows the QSF-PDD cage connector and then the cable down into the tank, right? And then we fill the trough up with fluid. Now we could take the variables out. So we get rid of you can see the SMAs and the traces are not exposed to fluid now. That's what we need to focus in on, what the pinpoints of the connector is. Likewise, we did the same thing with OSFP. We're working on that. And the interesting thing, we used a dielectric fluid to decay of 2.0, and we submersed it in the fluid for 3 days. Now we started to look at the data. We came back and we started to test this. But if you look now inside the pink box, the MCB trace is linear. There's no difference, obviously, because there's no exposure to fluid. But one of the things we're noticing is about an 18 ohm drop at the mated connector area. That is one of the attributes we need to overcome. And then if you look farther going down across the paddle card looks okay, but it's around the cable termination. So these are areas we needed to focus on. If its cable termination changes about 15 ohms, what are we going to do to the cable assembly in the future? Do we have to encapsulate the cable termination? Those sorts of things we need to try to learn. And that's why we want to show these fixtures. We can take out those unwanted variables from the very beginning, okay? Likewise, we're working on MCIO. This is, next steps. We're looking to do a MCIO vertical connector. Here's a top view. You could see the trough where we put the fluid in. And then likewise for MCIO right angle connector. So these are connector fixtures you can design for any form factor that you don't have to lock yourself in and just change your MCB. So these are, 4 form factors already. And then the last thing we wanted to show is the fluid effect on impedance. Depending on the fluid provider, some may be variable difference. We actually tested, raised the temperature to 55 degrees C, and we did see about a 3 to 4 ohm drop in impedance because of the viscosity changes. And then lastly, we did test it in air. We also showed PAM4I in air, and then in fluid we saw degradation. But Kai will briefly talk about also, we tested the bitter error rate. We saw degradation from about e to the -8 to e to the -5. So we could get it to work at 112, but thinking 224 is going to be the next challenge, though. Okay, back to you, Kai.
So this is eye diagram. This is a signal integrity people do what we care because it's really fast. So the tiny difference will have impact on the signal integrity and the working load performance. This is test 112 gigapalm4 per lane performance of Ethernet. The GPU to GPU also use 112. And the latest one uses 224 per lane. So we can see the blue one. Blue is what we test the channel in air, different channel with DAC cable. and OSIP, QSIP. And the red one is put into the common liquid immersion. So the dielectric reflection shows here, but it's still above the IEEE bit error rate line, the spec line, the purple color is the line. But we can see it's really reducing the margin we have, and it's about to fail. So that's so far the SI working group has been concluded that below 112 is kind of okay, but we need to test the PCIe Gen 6 now. In the 112 is a boundary now. About 112, 224, really need everybody to contribute. However, we know that it's due to the impedance reflection of the connector. Connector is exposed, connector cable exposed to liquid. So connector cable company can tune the impedance, redesign it to make a immersion specific connector. For example, this is an example that is EXE Max by Amphenol ARC. EXE Max ARC that redesigned for immersion can work better in PCIe 6 and maybe future for PCIe 7. That's how we need to work with Interconnect company. Basically, it's to fine-tune the impedance. Again, the impact is due to the high speed, really the high speed 112, 224, the Ethernet, and the GPU interconnection. Other than that, the low speed, is the impact is very limited. Give us the confidence, and also we have a path moving forward. This is Terry can tell us the fine-tune the impedance, their daily job.
Yeah, basically, we realize that the fluid effect is going to change, and we know that this is critical, right? And I think basically just the takeaways: limit the design, expose conductors. Obviously, the impedance is critical. We mentioned this many times. I think the biggest challenge we saw 112 we can see it. Performance, we're still within the spec limit line, but when we go to IEEE 802.3 DJ at 224 gig, it's going to be a lot of work. And so we need input from all of the members. So that's critical. And I think call to action, right? Call to action is basically, get involved for procedures for testing, and join the work stream and the meetings, and also sign up to the mailing list. These are the links here for, and also the email addresses for our work stream, right? So I think that's it. Thank you. Any questions?
For the ester type oil, ester has even higher decay value, so it could be approached in the similar method with the hydrocarbon type.
Are we talking temperature or SI performance?
Decay value of the ester type immersion cooling fluid.
Right.
Has
this was
a higher decay value.
Oh, if it's a higher decay. So this was 2.0. I think if it's a higher, it's obviously going to
3 or 3.5.
Yeah, the impedance will be lower for sure. Yeah.
I doubt it will work in 112. I think you can have the method test it, give us a more concrete number, but it's really in the high end.
So we would be welcome for follow-up with your discussion, and we can communicate that. Thanks.